In this video, we'll discuss how to use what we know about semidirect products to classify groups of order 12. So this is an example we've talked about a lot already. So let me just first review what we know. So if G is a group of order 12, we showed that either G has a normal Sylow II subgroup or it has a normal Sylow III subgroup. Why is that? Well, Sylow's theorem says that N2 is congruent to 1 mod 2 and N2 divides 3. So N2 is 1 or 3. N3 is congruent to 1 mod 3 and N3 divides 4. So N3 is 1 or 4. But if N3 is 4, then G has 4 times 3 minus 1 has 8 elements of order 3. So there are only 4 elements left. And the Sylow II subgroup of G has 4 elements. And it doesn't have any of these elements of order 3. So these remaining 4 elements must be a Sylow II subgroup. But if we had more than one Sylow II subgroup, we'd need to have some other place to find some elements not in this subgroup that could go into a different Sylow II subgroup. But there are no elements left. So this Sylow II subgroup is unique. So what have we seen? Either N3 is equal to 1 or N3 is equal to 4 and N2 is equal to 1. All right, we actually proved something better. So we proved that either N3 is equal to 1 or we zoomed in more carefully on the case where N2 is equal to 1. And we showed that in that case, G is isomorphic to A4. OK, so let's forget about this for now. And let's look at how to classify groups of order 12 using semidirect products. So let's say V is a Sylow II subgroup and T is a Sylow III subgroup. So V has order 4, T has order 3. By Lagrange, the intersection of these two subgroups is trivial. So the size of the set of products is 12, which is all of G. So the size of the set of products is G. At least one of these two subgroups is normal. Right? So that means that this VT is a group. But that also tells us that we can apply the recognition theorem for semidirect products. The G has to be isomorphic to a semidirect product. And now the order that we write it in matters because we don't know which one of V and T is the normal subgroup. So how are we going to understand how to classify all groups of order 12? Well, we'll just divide it into cases. We'll say, all right, if V is normal, then G is isomorphic to V semidirect product T with respect to some homomorphism phi from T to aught V. So V has order 4. We know what the two possibilities for V are. T has order 3. T is isomorphic to Z mod 3Z. Then we'll just switch and say, OK, maybe T is normal. And then G is isomorphic to T semidirect product V with respect to some phi, where phi is some homomorphism from V to the automorphism group of T. So I'll pause and erase and then show you how to carry out the details of this process. Let's continue this discussion of classifying groups of order 12. So we have a Sylow III subgroup, T, which is isomorphic to Z mod 3Z, and a Sylow II subgroup V, which has order 4. So it's either isomorphic to Z mod 4Z or it's isomorphic to Z mod 2Z cross Z mod 2Z. We know that either T or V, or maybe both, are normal in G. And that allowed us to apply the recognition theorem for semidirect products. So now, to understand what kind of group G is isomorphic to, let's break things up into cases. The first case we'll consider is when V is normal in G. So we've already seen that G is isomorphic to V semidirect product T with respect to some homomorphism phi, which goes from T to aught V. If V is isomorphic to Z mod 4Z, then the automorphism group of V is isomorphic to Z mod 4Z star, which is isomorphic to Z mod 2Z. In particular, the important thing is that the order of aught V is 2. T has order 3. Aught V has order 2. So those orders are relatively prime. So we've seen that that implies that there are no non-trivial homomorphisms from T to aught V. So what does that mean? in this case, where V is Z mod 4Z, V semidirect product T with respect to phi is isomorphic to the direct product of V and T because there's no choice for phi except the trivial homomorphism. Z mod 4Z cross Z mod 3Z is isomorphic to Z mod 12Z. And that's it. So now let's consider the other possibility for V, right? If V is not isomorphic to Z mod 4Z, then it's isomorphic to Z mod 2Z cross Z mod 2Z. Well, if that's what V is, then ought V is isomorphic to GL2 Z mod 2Z. And what does that group look like? Well, what's the order of the group? The order, remember we computed the order of GLN Z mod PZ by saying you can pick the first column of this matrix to be anything that's not 0, 2 squared minus 1 choices, and then pick the second column to be anything that's not in the span of the first column. So 2 squared minus 2 choices. That gives 3 times 2 total matrices. So GL2 Z mod 2Z is a group of order 6. It's easy to see that it's non-abelian. Just multiply like, I don't know, like a random pair of these matrices together. And most of the time you'll see that they don't commute with each other. So this is a non-abelian group of order 6. But we already classified groups of order 6. There's exactly one non-abelian group of order 6 up to isomorphism. This means GL2 Z mod 2Z is isomorphic to S3. Okay, so where are we in this case? Let's say T, this group of order 3, is generated by Y, some element of order 3. And we want to understand homomorphisms, phi from T to ought V, which we know is isomorphic to S3. Well, such a homomorphism is determined by where it sends a generator of T. So we just have to say, like, what is this automorphism phi Y? And Y has order 3. So phi Y has order dividing 3. So if this homomorphism is not trivial, then phi Y has order not 1. So phi Y has to have order 3. And now we know what the elements of order 3 in S3 look like. There are 2 of them. They are pick your favorite 3 cycle and then square it. Okay, so I'll pause and erase, and I'll tell you now we have 2 different homomorphisms that are non-trivial from T to ought V, and I'll tell you what happens when you take those semidirect products. Let's continue our discussion of this example where V is normal in G and V is isomorphic to Z mod 2Z cross Z mod 2Z. So we've seen that ought V is isomorphic to S3. T, this Sylow III subgroup, is generated by Y. And we want a non-trivial homomorphism from T to ought V. Y has order 3. So if this is non-trivial, where do you send Y? You send it to some automorphism of order 3. So ought V is isomorphic to S3. So ought V has exactly 2 elements of order 3 because S3 does. The elements of order 3 in S3 correspond to gamma and gamma squared, where gamma in S3 is some 3 cycle. So let's say phi I is the homomorphism from T to ought V determined by sending Y to gamma to the I. So we have 2 of these. You could also take I equals 0, which would give you the trivial homomorphism. So if you take these 2 non-trivial ones, where you either send Y to gamma or Y to gamma squared, the semidirect products you get are isomorphic. And you can see this using either exercise 6 of section 5.5, which we did on the homework, which was about, this semidirect products of H and K, where K was a cyclic group and the images were these conjugate subgroups. Or you can use lemma 6.2 in Conrad's notes, which is also about when 2 semidirect products are isomorphic. All right, so we get these 2 isomorphic semidirect products. What do they look like? Well, in this case, this semidirect product is isomorphic to A4. And I'll leave the details of actually writing down an isomorphism from this semidirect product to A4 as an exercise for you. All right, so that completely handles the case where V is normal in G. So what do we have to do now? We have to go back and say, well, okay, what if the Sylow III subgroup is normal in G? And then we have to consider all the possible semidirect products. So I'll pause and erase, and then we'll go through the details. Let's move on to the other big case in the classification of groups of order 12, where T is a normal subgroup of G. So T is the Sylow III subgroup. It's isomorphic to Z mod 3Z. What does the automorphism group look like? Well, it's isomorphic to Z mod 3Z star, which is an abelian group of order 2, so it's isomorphic to Z mod 2Z. So let's name a generator for this group. So let's call it lambda. So lambda is this automorphism of T of order 2. And what we need to do is consider all the possible homomorphisms phi from V to aught T. And what those homomorphisms are, that's going to depend on which group V is. So we know that it's a group of order 4, so we split it into two cases. So if V is isomorphic to Z mod 4Z, let's pick a generator. Let's say that V is generated by X. So there's exactly one non-trivial homomorphism phi from V to aught T, because a homomorphism is determined by where you send this generator X. So we can either send X to the identity of aught T, in which case we get the trivial homomorphism, or we can send it to the other thing. We can send it to the non-identity element, lambda. So what group do we get here? Well, this is an example we talked about in an earlier lecture on direct products. So this is example 2 from page 178 of Dummett and Foote. We get this non-abelian group of order 12 that's not isomorphic to D12 or A4. Okay, now let's consider the other possibility. If V is isomorphic to Z mod 2Z cross Z mod 2Z, and let's name some generators. So let's say V is generated by A and B, that we have these two independent elements of order 2, or rather that V is isomorphic to the direct product of A and B. There are 3 non-trivial homomorphisms from Z mod 2Z cross Z mod 2Z to Z mod 2Z. So how do we know that? Well, if you have a homomorphism that's non-trivial, then it's surjective. So that means that you have this group of order 4, this surjective homomorphism. It's determined by saying what is the kernel of this homomorphism. Well, it's some subgroup of Z mod 2Z cross Z mod 2Z of order 2. And there are 3 different choices. There are 3 distinct subgroups of order 2 in this group, and each one gives a different non-trivial homomorphism to Z mod 2Z. So I claim that all 3 of the semidirect products you get from these 3 different homomorphisms are isomorphic to each other. And here's a case where really it's better to use lemma 6.2 in Conrad's notes about when semidirect products are isomorphic, because that exercise, exercise 6 of section 5.5, only applies to the case where you're taking a homomorphism from K to aught H, where K is cyclic. So yeah, so these semidirect products really are all isomorphic, and you can check that. All right, so now let's just pick our favorite one. Let's say, where do you send phi of A comma 0? Let's send that to the identity of Z mod 2Z, and phi of 0 comma B, let's send that to the non-identity element of Z mod 2Z. So here I guess I'm being a little informal. Lambda is our non-identity element of aught T, which here I've written this just as Z mod 2Z. So what is this group that we get here? Oh, now I realize I've made a mistake, that this should say T is the normal one. So what is this group that we get here? T semidirect product V with respect to phi. I'll pause and erase, and then we'll see how to recognize this group as one that we already know. Let's finish this classification of groups of order 12. We have this homomorphism, which sends A0 to the identity element and 0B to the non-identity element in aught T. So what is the corresponding semidirect product? Well, okay, so what are we looking at? A semidirect product of Z mod 3Z and Z mod 2Z cross Z mod 2Z determined by this homomorphism. So let's look inside this semidirect product. And we can find a subgroup isomorphic to Z mod 2Z, which is 0 in the Z mod 3Z component, whatever in the first of the Z mod 2Z components, and 0 in the second one. What's special about the first component? That's the one where our homomorphism is just sending it to the identity element in aught T. And then we have another subgroup that's isomorphic to D6. So it's whatever in the Z mod 3Z component, 0 in this first Z mod 2Z component, and Y, whatever, in this second component. This is the component where the homomorphism phi is sending 0b to some non-trivial automorphism of T. So we see that this is actually a subgroup that's non-abelian. This is just like the what came up in the classification of groups of order 30, which goes all the way back to this first example of recognizing dihedral groups as semidirect products. So now, these subgroups are both normal. I mean, the first one is easy to check. This second one has index 2 in this group of order 12, so it's automatically normal. And we can apply the recognition theorem for direct products to see that this semidirect product is isomorphic to Z mod 2Z cross D6. So now we've gone through all the cases, and we've seen that every non-abelian group of order 12 is isomorphic to either A4 or this new non-abelian group of order 12 that we saw in case 2a. So this is one that we had seen in a previous lecture. Or in this last case, we get Z mod 2Z cross D6. All right, so there's one thing though, which is I know another non-abelian group of order 12, which is D12. So D12 has to be isomorphic to one of these three. And okay, well, we know that D12 is not isomorphic to A4. We already saw actually that it's not isomorphic to this non-abelian one from order case 2a. So it has to be isomorphic to Z mod 2Z cross D6. But why is that? Well, 12 is 2 squared times an odd number. So 12 is 4 times n, where n is an odd number. And in example 1 on page 172 of Dummett and Foote, where we talked about the recognition theorem for direct products, we saw that in this case, D4n was isomorphic to D2n cross Z mod 2Z. So this is one instance of that fact. Okay, so a lot went into this. We had to recognize that, okay, the abelian groups of order 12, easy to classify. The non-abelian ones, we saw that we could write them all as semidirect products of a Sylow II subgroup and a Sylow III subgroup. There were two possibilities for the Sylow II subgroup. And then we didn't know which one of the two, the Sylow II subgroup or the Sylow III subgroup, was normal. So in some sense, we had 4 cases to go through. T is normal, V was equal to Z mod 4Z, or V was equal to Z2 cross Z2, or V is normal, and then we had to split up into those 2 cases.